September 2024. Astronomers analyzing data from the James Webb Space Telescope detected light from an object that shouldn't exist according to our understanding of physics. This light has been traveling toward us for 13.5 billion years. It left its source just 300 million years after the Big Bang, when the universe was still an infant, when the first stars were just beginning to ignite. But here's what made the entire astronomy community go silent. The light contains information, patterns, structures that suggest organization, complexity, processes that should have taken billions of years to develop. We're not just looking back in time, we're looking at the edge of time itself, the boundary between existence and nothing. And what we're seeing there changes everything we thought we knew about the beginning. The James Webb Space Telescope isn't just looking far away, it's looking back in time. And to understand why that's possible, we need to talk about what distance means in an expanding universe. Light travels at 186,000 miles per second. That's fast, but space is incomprehensibly huge. When you look at the sun, you're seeing it as it was 8 minutes ago because that's how long light takes to travel 93 million miles. Look at the nearest star beyond our solar system, Proxima Centauri, and you're seeing 4 years into the past. Look at the Andromeda galaxy, 2.5 million years. The further you look, the further back in time you see. The most distant objects Hubble could clearly observe existed about 400 million years after the Big Bang. That was impressive, pushing the limits of what visible and near-infrared astronomy could achieve. But Webb was designed to shatter that limit. Its 21-foot gold-plated mirror collects infrared light that's been stretched by cosmic expansion into wavelengths Hubble couldn't detect. It sits at Lagrange point 2, a million miles from Earth, where its massive sun shield keeps it colder than negative 380 degrees Fahrenheit. This extreme cooling is critical. Infrared astronomy requires the telescope itself to be colder than the objects it's observing. Otherwise, the telescope's own heat radiation would overwhelm the faint signals from distant galaxies. When Webb turned on its instruments and began observing the deep universe, it was designed to see the first galaxies forming, the cosmic dawn when stars first ignited and light flooded the primordial darkness. What it saw was far stranger than anyone predicted. In July 2022, Webb's first deep field image was released. Thousands of galaxies, some of the oldest ever observed, packed into a tiny patch of sky. Astronomers immediately began analyzing the most distant objects, measuring their redshift to calculate how far away they were. That's when the anomalies started appearing. Objects that were too bright, too massive, too organized for their age. Galaxies that looked mature when they should have been chaotic clouds of gas. Structures that required billions of years to form, appearing in a universe only hundreds of millions of years old. But in September 2024, Webb detected something that pushed beyond anomaly into genuine crisis. An object so distant that its light had been traveling for 13.5 billion years, placing it at the very edge of the observable universe. This object, designated JWST 14O, exists at redshift Z1432. That means we're seeing it as it was just 290 million years after the Big Bang. To put that in perspective, if the universe's 13.8 billion year history was compressed into a single year, we're looking at January 2nd. The cosmic calendar had barely started, and yet this object was already there, already shining, already complex. To understand why finding anything at this distance is shocking, we need to talk about the period between the Big Bang and the first stars. Astronomers call it the cosmic dark ages. The Big Bang happened 13.8 billion years ago. In the first moments, the universe was unimaginably hot and dense, pure energy, no atoms, no matter as we know it, just a seething plasma of fundamental particles. As the universe expanded, it cooled. About 380,000 years after the Big Bang, it had cooled enough for electrons and protons to combine into hydrogen atoms. This is called recombination, and it's when the cosmic microwave background radiation was released. After recombination, the universe entered darkness. There were no stars yet, no galaxies, just vast clouds of hydrogen and helium, drifting in the expanding cosmos, cooling, slowly collapsing under gravity. This darkness lasted for hundreds of millions of years. Gravity pulled gas clouds together. Denser regions grew denser. Eventually, the pressure and temperature in the cores of these clouds became high enough to ignite nuclear fusion. The first stars were born. These weren't stars like our sun. They were massive, hundreds of times the sun's mass, burning incredibly hot and bright. They lived fast and died young, exploding as supernovae after just a few million years. But in their brief lifetimes, they did something crucial. They created heavy elements. Carbon, oxygen, iron, all the elements heavier than hydrogen and helium were forged in the cores of these first stars and scattered across space when they exploded. Second-generation stars formed from this enriched material. These stars could form planets. These stars could develop the chemistry needed for life. Our sun is a third or fourth-generation star, made from the recycled remains of stars that died billions of years ago. According to our models, this process of first stars forming, dying, enriching space, and allowing second-generation stars and galaxies to develop should take at least 500 million years, probably closer to a billion. But JWST Z14O exists at 290 million years. Before the process should be complete. Before galaxies should have time to form and organize. And it's not just existing. It's bright. It's structured. It's already gone through multiple generations of star formation based on its spectral signature. It's like finding a fully grown oak tree sprouting from soil that was bare dirt yesterday. When astronomers analyze light from distant objects, they're not just measuring brightness, they're reading a cosmic fingerprint that reveals composition, temperature, age, and motion. Light from JWST Z14O passed through Webb's spectrograph, which splits light into its component wavelengths. This creates a spectrum showing exactly which elements are present in the object. What they found was shocking. The spectrum showed heavy elements, carbon, oxygen, maybe even iron, elements that should not exist in significant quantities this early in cosmic history. The only way to create these elements is through stellar nucleosynthesis, the fusion processes inside stars, and through supernovae explosions. That means multiple generations of stars had already lived and died by the time we're observing this object. But there wasn't enough time. From the Big Bang to this observation point is only 290 million years. The first stars probably formed around 150 million years after the Big Bang. That gives maybe 150 million years for stars to form, evolve, explode, enrich space with heavy elements, and form new stars from that enriched material. Current stellar evolution models say this process takes at least 500 million years. The math doesn't work. Then there's the object's luminosity. It's incredibly bright, suggesting a massive galaxy with billions of stars, or possibly an active galactic nucleus powered by a supermassive black hole. If it's a galaxy, those billions of stars shouldn't have had time to form. If it's a black hole, that black hole shouldn't have had time to grow to supermassive size. Either way, something is wrong with our timeline. Dr. Brant Robertson from UC Santa Cruz, part of the team that confirmed the discovery, said, "We're seeing things that challenge our fundamental understanding of how the universe evolved. It's not just one or two objects anymore, it's systematic. The early universe was far more active than our models predicted." But there's something even stranger in the data. The spectrum shows absorption lines, dark bands where specific wavelengths are missing because they were absorbed by intervening material. Analyzing these absorption lines can reveal what's between us and the distant object. In this case, the absorption pattern is unusual. Some of the intervening material seems to have chemical signatures that don't match standard cosmic evolution models. It's as if the space between us and this ancient object contains structures, clouds, or regions with unexpected composition. One team analyzing the data found periodic variations in the absorption pattern, regularities that could suggest large-scale structures in the early universe that shouldn't exist yet. The cosmic web, the vast filamentary network of dark matter and gas connecting galaxies, shouldn't be organized this early. But the absorption data hints that it might be. JWST Z14O sits near the boundary of what's called the observable universe. Not because there's nothing beyond it, but because light from anything further hasn't had time to reach us yet. The universe is 13.8 billion years old. Light travels at a fixed speed, so logically, we should only be able to see objects up to 13.8 billion light years away. Right? Wrong. Because the universe is expanding, the actual radius of the observable universe is about 46.5 billion light years. Objects we see at extreme distances have been carried away from us by cosmic expansion while their light was traveling toward us. This creates a boundary called the particle horizon. Beyond this horizon, light has not had time to reach us since the Big Bang. It's not that nothing exists there, it's that we cannot observe it. Information from beyond the particle horizon is fundamentally inaccessible. JWST Z14O is approaching this boundary. We're seeing it as it was 13.5 billion years ago, just 300 million years after the Big Bang. The light we're receiving left when the universe was 2% of its current age. But here's the unsettling part. We're not seeing the object as it is now. We can't. Due to cosmic expansion, that object is now roughly 30 billion light years away. We will never see what it looks like today because that information would take longer than the current age of the universe to reach us. We're observing a ghost, an echo from cosmic infancy. The object we're seeing might have evolved into a massive galaxy cluster by now, or it might have been destroyed in a galactic collision. We have no way of knowing. And if there are objects even further away, existing even earlier in cosmic history, their light might never reach us. They exist beyond our particle horizon, forever invisible, forever unknowable. This raises a profound question. How much of the universe's history are we missing? How many objects existed in the first 100 million years after the Big Bang that we'll never detect because their light hasn't reached us and never will? Some cosmologists estimate that for every galaxy we can observe, there might be hundreds or thousands beyond our horizon, participating in cosmic evolution we'll never witness. We're not seeing the whole story. We're seeing a limited sample, biased by our position in space and time. And the most distant objects, the ones pushing closest to the edge of observability, are the ones that challenge our models most severely. It's as if the universe is hiding its secrets at the boundaries of what we can detect, revealing just enough to confuse us, but not enough to provide answers. JWST Z14O is not alone in breaking the rules. Webb has found dozens of objects from the early universe that shouldn't exist according to standard cosmology. In 2023, astronomers discovered what they're calling Einstein's zigzag, a bizarre structure where light from a distant quasar has been bent by gravitational lensing in a pattern that reveals 6 different images of the same object. This happens when light passes near a massive galaxy cluster, which warps space and bends the light path. But the specific pattern of Einstein's zigzag suggests the intervening mass distribution is highly organized, with dark matter arranged in ways that seem almost artificial. Of course, it's not artificial, but the precision of the structure, the specific arrangement needed to create this lensing pattern, is statistically improbable. Finding one such arrangement is lucky. Finding multiple raises questions about whether our models of dark matter distribution are fundamentally wrong. Then there's the discovery of mature quasars in the early universe. Quasars are supermassive black holes actively feeding, shining brighter than entire galaxies. Webb found quasars existing 600–700 million years after the Big Bang. These black holes weigh billions of solar masses. Growing a black hole that large requires either 1. Starting with a massive seed black hole, which requires exotic physics we haven't observed. 2. Feeding continuously at or above the theoretical maximum rate for hundreds of millions of years. 3. Some unknown mechanism that accelerates black hole growth beyond known limits. None of these options fit comfortably within standard astrophysics. Dr. Fabio Pacucci from Harvard said, "These black holes are too big, too early. It's like finding a 10-year-old child who's already 6 feet tall and weighs 200 pounds. Something about their growth process is different from what we understand." And then there are the galaxy morphologies, shape and structure. Galaxies we observe in the modern universe come in distinct types: spirals like the Milky Way, ellipticals, irregulars. These shapes result from billions of years of gravitational interactions, mergers, and star formation. Early galaxies should be chaotic, messy, irregular. Gravity hasn't had time to organize them into elegant structures. But Webb is finding spiral galaxies, barred spirals, and other organized structures existing as early as 2 billion years after the Big Bang. Finding them at all this early is surprising. Finding them in such mature configurations is inexplicable. One galaxy, nicknamed Sparkler, shows a central bulge surrounded by what appear to be globular clusters, dense spherical collections of old stars. Globular clusters are thought to form early in a galaxy's history, but seeing them this organized, this early, challenges formation models. So what does it mean that James Webb photographed the edge of time itself? It means our models are incomplete. The Lambda CDM model, our standard cosmological framework, successfully explains cosmic microwave background radiation, large-scale structure, and the expansion rate. It works beautifully for the universe from about 1 billion years after the Big Bang to the present, but it's struggling with the earliest epochs. The first few 100 million years are revealing processes, structures, and timelines that don't fit the predictions. Either dark matter behaves differently in the early universe than we thought, or dark energy wasn't constant, or star formation was far more efficient, or our understanding of black hole formation is wrong, or some combination of all these factors plus others we haven't considered. This isn't a crisis that breaks cosmology, it's a refinement process. Science advances when observations challenge theories. Models get updated, understanding deepens. But there's something philosophically unsettling about what Webb is showing us. We're looking at light from objects so distant that the universe was barely started when that light began its journey. We're seeing the universe in its infancy, watching the first structures form, witnessing cosmic dawn. And what we're seeing is more complex, more organized, more advanced than it should be. It's as if the universe hit the ground running, starting faster and more sophisticated than our models predicted. Why? We don't know. Maybe the conditions in the early universe were radically different from what we assumed. Maybe the Big Bang itself was more complex than our models suggest. Maybe there are processes, forces, or phenomena operating in the early universe that left no trace we can detect in the modern cosmos. We're looking at the edge of time, the boundary between existence and the void before the Big Bang. And that boundary is showing us mysteries we're only beginning to unravel. James Webb photographed the edge of time. Light from 13.5 billion years ago. Light that left its source when the universe was 2% of its current age. Light carrying information about the first galaxies, the first stars, the cosmic dawn. And that light is telling us we were wrong. Not completely wrong, but wrong enough that our models need revision. The early universe was more active, more complex, more mysterious than we thought. As Webb continues observing, we'll find even more distant objects, pushing closer to the absolute boundary of observability. Each discovery will refine our understanding. Each anomaly will challenge our assumptions. We're living through a golden age of cosmology. The questions we're asking now are better than the questions we asked a decade ago. The answers we're finding are stranger than we imagined. Somewhere out there, at the very edge of the observable universe, light is traveling toward us from objects we haven't detected yet. Objects that formed even earlier, shone even brighter, existed even closer to the beginning of time. When that light reaches our telescopes, what will it show us? What secrets from the edge of time are still waiting to be discovered? What do you think is happening in the early universe that we don't understand? Drop your theories in the comments. And if you want more discoveries that challenge everything we thought we knew about the cosmos, subscribe. Because Webb is just getting started, and the edge of time has more secrets waiting to be revealed.